This course module covers the technical fundamentals of compact DP Flowmeters. After completing this module, you will be able to specify the DP flow technologies used in the compact DP Flowmeter family, describe the principle of operation that applies to orifice, integral orifice, and wedge, and how it is different from the principle that applies to an averaging Pitot. State the differences in the effect of temperature and pressure changes on the flow measurement of a liquid compared to measurement of a gas. List the advantages of multivariable transmitters over separate transmitters. DP meters generally do not require flow calibration because their design has evolved from many years of empirical testing and evaluation. This has led to technologies whose performance can usually be predicted by verifying dimensions and ensuring they meet the design standards. They can readily be fabricated in an unrivaled range of materials, including exotic alloys and even plastics. Their design and construction is easily adapted to cope with applications having elevated pressures and/or temperatures. The wide range of different DP technologies available means that a DP-based solution exists for the measurement of almost any liquid, gas, or vapor. The first of the three equations or laws that govern how the meters operate is the continuity equation. When applied to a flow meter, it can be expressed in a rather basic way as what goes in must come out. In other words, the flow rate at any point in the meter is a constant, so the flow rate at the inlet is the same as the flow rate in the middle and is the same as the flow rate at the outlet. As the fluid passes through a restriction like a venturi tube or orifice plate, it must accelerate because the volume flow rate stays the same, but the area it is passing through is smaller. Remember that the volume flow rate Q is the product of the area A and the average velocity V. So, a velocity in meters per second multiplied by an area in square meters gives a volume flow rate in cubic meters per second. The second applicable law is the law of conservation of energy, which says that energy cannot be created or destroyed, only changed from one form into another. Examples of such energy changes are all around us in everyday life. For example, a light bulb converts electricity into light, which is what we want, and also to some heat, which is not particularly desirable. Gas fires and solid fuel fires will both convert the chemical energy stored in the fuel into heat, the key requirement, and light, a secondary requirement. A dynamo or generator converts rotational energy into electricity, and also some heat. We've already shown that as a fluid passes through a restriction, it must accelerate. An increased fluid velocity, which means that its kinetic energy has increased, because the kinetic energy is proportional to the square of the velocity, i.e. half times m times v squared. This increased energy must come from some other form of energy present in the system. It actually comes from the pressure, which is therefore reduced in and around the restriction. So a local increase in velocity will produce a reduction in the local pressure. The same phenomenon happens with aerofoils, for example airplane wings, where the faster moving air above the wing creates there a lower pressure than that caused by the slower air below the wing, hence giving an upward force, called lift, to the wing. This is a demonstration of the third law governing the meter, Bernoulli's theorem, which confirms that for a flowing fluid, ignoring losses due to viscosity, compressibility, and turbulence, the sum of the energies in the stream due to pressure, velocity, and height above a datum level is a constant. If the medium to be measured flows through a pipeline whose cross-section is constricted by a primary device, the flow velocity at the restriction increases. The increase in flow energy causes a reduction in pressure energy. The pressure difference is called the differential pressure and is used as variable for the flow. Downstream of the primary device, the increased flow energy is reconverted to pressure energy. However, a part of the differential pressure is lost and is referred to as the permanent pressure loss. The proportion lost depends upon the type of restriction used and its relative diameter to the pipe. That means that it depends on the type of DP flow meter used and how much of a restriction to flow it produces. For a given DP flow meter technology, a smaller diameter restriction creates a larger DP. In addition, a larger percentage of that DP is lost. As pressure loss depends on the restriction shape, the internal profile of the meter, as well as on the pipe-to-restriction ratio of the primary device, it can be reduced to a minimum by the selection of the appropriate DP metering technology. When calculating the primary device, the physical properties of the fluid are assumed to be time constant. However, the actual properties often differ from the values taken as the basis for the calculation. In this case, it is necessary to correct the flow according to the variations of the properties. The correction can be made by recalculating the measured values, either manually or by a flow computer for automatic correction. When deciding whether the cost of an automatic correction is justified, it has to be assumed that for gases, a variation of the pressure or the temperature of 2% of the absolute value will itself result in a measuring error of 1% of the respective flow. For superheated steam, similar sources of error apply. In contrast, for liquids, the influence of pressure and temperature is considerably lower, meaning that in most cases a temperature correction alone is sufficient because the pressure has almost no influence on the density of the liquid. Now let's compare the physical principles of measuring gas or liquids. A DP generating flow element is mounted in the pipeline. Small bore pressure piping, called impulse piping, connects the element to a multi-valve manifold. The manifold is connected to a differential pressure transmitter, either by being bolted directly to it or via more impulse piping. Its main function is to allow easy zeroing of the transmitter under line pressure, as the zero calibration is more accurate when performed at line pressure. The DP generated is proportional to the square of the flow rate. The transmitter linearizes the measurement and emits a 4 to 20 milliamp signal representing 0 to 100% of the flow rate in the pipe. We will now focus on the DP technologies that are supplied in our compact DP flow meter family. We start with the Orifice plate, where there are many different designs, but in the compact family, and in most applications generally, the restriction typically consists of a plate with a central hole, with a sharp edge at the inlet. Describing the characteristics of an Orifice system, note that the Orifice is still an industry standard, and the most studied primary device, because it uses a simple design. We can see this if we just look inside. It is very simple to manufacture and therefore available for a reasonable price. The price increases relatively slowly with increasing diameter. Due to the simple construction, the costs are comparatively low. The advantage is that all kinds of liquids, gases, and even steam can be measured using Orifice meters. Sometimes, however, the relatively high permanent pressure loss of Orifice plates could be a disadvantage. The integral orifice is an orifice assembly designed for small pipe sizes and relatively low flow rates. The characteristics are that it is much more complex to manufacture, as it involves not only a small orifice plate but also a mounting assembly, and often upstream and downstream pipework with flanges. Consequently, it is considerably more expensive. But it is very versatile, because it can meter fluids in small pipelines and be supplied with replaceable orifice plates, which come with a selection of predetermined bores. This enables a standard product to be able to be applied to a wide range of fluids and flow rates. The advantage is that relatively low flow rates of clean liquids and gases can be measured. Sometimes the relatively high permanent pressure loss could be a disadvantage, and the design is outside of the major international DP Flowmeter standards. Wedge meters are particularly suited to the measurement of viscous and/or erosive fluids. The restriction is V-shaped, hence the name wedge, on one side of the pipe, and it is characterized by the H/D ratio, which is the opening under the wedge divided by the internal meter diameter. Unlike an orifice plate, the performance of the wedge does not rely on maintaining sharp edges. It has a higher purchase price than an orifice plate and is still expensive to install. Its advantages are that it is robust and that it maintains its meter factor down to much lower Reynolds numbers than most other DP devices, down to Reynolds numbers as low as 500 in fact. The wedge element allows the passage of solids in the fluid. It requires shorter upstream pipe lengths than many DP devices, down to only 5 pipe diameters long or even shorter. It is, however, quite a bulky meter with a relatively high pressure loss. A Pitot tube operates in accordance with the same basic laws as an orifice plate, but in a slightly different way. Here we will examine the differences between the two. As the energy in a fluid stream through a meter is constant, then the sum of the 3 basic energy types present, kinetic energy, energy of motion, potential energy, energy of position or height, and pressure energy, is also a constant, ignoring friction losses. In an orifice or venturi, the fluid mass is accelerated through a restriction, which is why such types are often referred to as mass acceleration devices. We have already seen that this acceleration causes the conversion of pressure energy to kinetic energy and creates a region where the local pressure is lower than the overall static pressure. With a Pitot tube, there is no acceleration of the fluid. A probe is inserted into the flow with the sensing port or ports pointing into the flow stream. Some of the fluid's kinetic energy is converted to pressure energy at the high-pressure tapping, where the flow impacts on the probe, creating a point where the sensed pressure is slightly higher than the overall static pressure. This energy conversion is the opposite of that in most other DP flow devices, where pressure energy is converted to kinetic energy. A simple Pitot tube measures flow at only one small point in the pipe, and, to ensure this is representative of the average velocity in the pipe, the relationship between velocity and insertion depth into the pipe needs to be mapped using a process called traversing, so that the location where the point velocity is equivalent to the average or mean velocity can be found. So, as you can see, averaging Pitot and orifice devices operate according to the same laws, but involve different energy conversions. We have seen that single-point Pitot tubes require traversing to find the location of the point of mean velocity. Averaging Pitot tubes have multiple upstream holes to measure the flow at several points across the pipe diameter. The impact pressures across the pipe are combined to give an average upstream pressure, which relates to the average flow velocity, in other words, the true flow rate. A separate hole, not facing into the flow stream, effectively measures the static pressure alone. The averaging removes the requirement to perform a traverse across the flow profile. The difference between the impact, high, and static, low pressures is proportional to the flow rate. One advantage of averaging Pitot tubes is that typically the meter is installed via a single hole drilled in the pipe wall, so it has a low installation cost. In addition, it creates only a very small obstruction in the pipe and therefore incurs a very low pressure loss. However, it only generates a relatively small DP value compared with other DP devices. So now you see how the averaging Pitot tube measures the mean fluid velocity without the need for traversing. Real problems are solved using these compact DP Flowmeters. All of the pitfalls shown here are real issues, identified in best practice guides such as this TUV NEL publication. And all of these are either removed completely or at least reduced by using compact DP Flowmeters. Here is a basic comparison of some of the major DP flow metering technologies used in compact DP Flowmeters. The key points are: Orifice devices are typically low cost, but are often expensive to install, are susceptible to wear, and create a relatively high pressure loss. Integral orifice meters are designed for low flow rates, but are generally not suitable for steam measurement. Averaging Pitot tubes incur a very low pressure loss and can be installed at relatively low cost, but they generate a small differential pressure. Wedge meters will measure liquids that are slurries and/or are viscous, but are quite large in size and weight. Venturi meters are particularly robust and only incur a small pressure loss, but they have a long installation or lay length and are expensive. In conclusion, we can say that DP flow devices will measure most combinations of fluid type, process pressure, and working temperature. Now, let's summarize this learning module. So, what have you learned so far? The compact DP Flowmeter family uses orifice, integral orifice, wedge, and averaging Pitot tube technologies. Orifice, integral orifice, and wedge are mass accelerators and convert pressure energy to kinetic energy. Averaging Pitot tubes, however, convert the kinetic energy from the fluid impacting on the meter to pressure. All DP devices will cause a permanent loss of pressure in the system, but careful selection of the DP technology used and its design can reduce the overall pressure losses.